I have the I have the dark side hat.
Yes, you do.
So did everybody just get the recording notice?
Yep.
Okay.
Yes.
All right. As much as possible, I would love it if you keep yourselves unmuted. So if you want to make a comment, point out, add a clarification, add some extra information, whatever, it would be nice if we can hear you. So please do that if you can. So first of all, I just wanted to say this is kind of a trial balloon. I think, if you look at our astronomy section, there's groups of people that are quite active and some that are not. There's kind of like a silent majority, and we don't know exactly what they're all up to, but we have imagers and we see a lot of their stuff because they're always emailing us and showing us their great images. And there's the observers, and then, there's a pretty finite group of people that show up at Fair Center regularly, right, Mark?
Yeah.
And then there's the outreachers, which are kind of, an additional group of people that don't do so much observing for themselves, but they do it for other people. And then there's the silent majority, and we don't know too much about them, but we do know that there's constant turnover of new members, and as well as people who don't have maybe formal education in astronomy. And so the idea was, let's start something, let's see how this works. And so tonight is just one example of what we might do. All the questions about what kind of topics should we cover and when and how in what depth and at what level and all that. Hopefully that's all going to work its way out. But my vision is none of this is like college level material. Certainly not anybody who's an astronomy major. Maybe the people that are How do you get your comments to show like that, Michael? Can we all do that?
He's got him on the side.
That was yeah, okay, I see. So that is the chat over there?
Yeah.
Okay, I didn't realize that was a chat. Good, I'm glad to see it. Anyway, so it's just an example. I'm hoping actually that a number of the people that are on the call tonight, you know who you are, might be willing and able to do a future program. It would be nice if we kind of got into a cadence of like once a month or thereabout, if there's an interest. And I do think once we started that there might be a growing population of people that think, gee, I could tune in and learn something. So that's my hope. I tried to make tonight's program pretty varied in terms of what we're seeing and doing. So I hope you like it. We'll take a checkpoint now and then and see if anybody's fallen asleep or whatever. Hope you won't. And that's it. Any comments as we start?
I'd like to insert a blurb about this in the welcome to new members that I send out.
Okay.
We invite them to join the Google group and all that stuff, but it'd be nice to send this out to people who are, don't describe themselves as professional astronomers, that this is a good way to get involved and learn something right away.
Yeah.
And meet like-minded or like experienced people. So I'll go over that with you maybe at the next board meeting so we can start that.
Okay. This is water, not wine. Wine will be later. Tom Race, hi there. Just saw you pop on. If you can unmute yourself, as much as possible, just so you can interject and respond and query and all that, whatever. Okay, so hopefully I'm going to share my screen, and it's going to take us to screen sharing, share. Okay, hopefully what you all see is the screen that says gravity and orbits. Do you?
Yes.
Great, perfect. We're on a roll. Okay, so we're going to talk about gravity and orbits on a fairly high level. I'm sorry, high. I don't mean high. I mean
unintended.
A what? Not in depth. Not in depth. This is not the graduate course. This is I think everybody can tune into everything that's going to go on. And because it's such an important topic, gravity. We're all about gravity, right? Whoops. All right.
It's what grounds us.
There we go. Now I have to move people around so I can see my screen. Okay, so gravity, it's a fundamental force that formed the universe, forms it still. It makes the worlds go round, and it makes the worlds round. So we're going to talk about that, and this is kind of the agenda, if you will. We'll see how many of you stay on for the. So first we're going to talk about the math of gravity and the nature of orbits somewhat, and then we're going to actually use a couple of movie clips to perhaps point a little hole in how the movies might have portrayed something about gravity. We're going to do a very brief recap of some of the major contributors to our understanding of gravity and the motions of worlds. There would typically be several long lectures in a college or even, I think, in a high school course. So this is going to be just touching on it, but because I want to put a couple things in context. First of all, the gravity equation that we're going to start with, and also something that comes later, which is the next point, a special focus on the early observatory of two of those astronomers who are the most important in this whole growing, developing understanding of gravity, motions, and the basis of astronomy. And then finally, if we get to it and you're still with me, just because it'd be fun to have a topic to kind of kick around, the one I chose is a chance to imagine the impacts on human existence while we're under the threat of the impact of a large asteroid that's incoming to Earth. You'd hope the number one thing would be let's stop it. But anyway, so let's go on from there. All right, so you may or may not, you probably all do know that Martin Rees is the Astronomer Royal of Britain, and a lot of other things. I guess I have a question in my mind right now. Is he still living? Michael, do you know the answer to that? Is he still living? If you can see his comment, I can't see it. What's that?
Michael doesn't know.
Michael doesn't know. Okay. Anyway, a brilliant guy, and there's a wonderful book. If you haven't ever read Just Six Numbers, you should read it. It's a great book, and you don't have to be a cosmologist to get a lot out of it. But it's about how the numbers and quantities that form the physics of our universe are very fine-tuned. Anyway, so these are his comments on gravity that I thought were important to start with. Gravity grips planets in their orbits and holds the stars together. On a larger scale, entire galaxies, swarms of billions of stars are governed by gravity. No substance, no kind of particle, not even light itself, escapes its grasp. It controls the expansion of the entire universe and perhaps its eventual fate. And then, despite its importance for us, for our biosphere and for the cosmos, gravity is actually amazingly feeble compared with the other forces that affect atoms. How then can gravity nonetheless be dominant, pinning us to the ground and holding the moon and planets in their courses? It's because gravity is always an attraction, as opposed to the other forces that have opposing components. So with that as a background, any comments anybody wants to make?
He's still alive.
He's still alive. Thank you for checking. I'm glad he is. I think he's an older gentleman though.
Yes.
Okay, we're going to start right kind of at the end, well, at least toward the end of the understanding of gravity. Isaac Newton discovered this mathematical understanding of gravity. Wow. Can you see the whole? You probably can't see the whole slide. Or can you?
Yeah, we can see the whole
I
slide.
think we can.
Okay. All right, good. I have people in the way, so that was my problem. And so if you're used to working with equations, this will be instantly viable. And if you haven't done it in a few years or decades, like some of us, let's go through what it means. So the equation is this. There's a gravitational constant called G. And if you multiply that by the mass of two objects that are gravitationally bound, and then you divide that by the square of the distance between them, you get the force of gravity. So the G is that gravitational constant, which is just a constant of nature. It's built into the physics. And the masses are usually in terms of kilograms or whatever is appropriate to match with G. And the R is the distance between them from one center of gravity to the other center of gravity. So, and what this equation says is that is either or both of the masses increase, the force of gravity increases proportionally. So, think of it as M1 is the Earth maybe, and M2 is, and if either one of those two bodies had greater mass, it would increase the amount of gravity. And then as the distance between them increases, the force of gravity decreases proportional to the square. So simple enough, right? Okay, just this is a little bit more about it. It's always it's an attractive force, the weakest force in nature, but as our astronomer Royal said, despite that, because it's always attractive, it's a very important force. It depends on the masses and on the inverse square law. We'll talk about that in a second. And G is this universal gravitational constant. G applies throughout in any gravitational situation. And gravity extends forever. So you can't, there have been movies where they've said they get beyond the gravitational force of Earth. Well, you never really get beyond because gravity extends forever. And then if you take a look at that little graph, I don't know, can you see my cursor?
Yes.
Okay, so this little graph, I always have a problem in our talks at our regular meetings if somebody throws up a graph like with a logarithmic scale and all kinds of undecipherable things on the axis, and they don't tell us what they are, and we're supposed to derive a meaning from it. But this is a pretty simple graph. So the force of gravity is rising over here on this axis. It's just from a starting point of 1, how does it decrease? And this is talking about as distance, 1 radius. So that would be like the Earth Moon distance, and then 2 radii would be if you move the moon twice as far away, and so on. And so you can see how it dramatically decreases according to the distance because you're squaring the distance. Okay, pretty simple. Hey, Don.
Hi there.
Hi.
You hear me?
I do. Let me
Yeah.
just, did we have anybody else come on that I'm just taking a quick look? Tom Race, he said hi to you, I think. Yeah, that looks like it. Okay, great. Don will be a major contributor in a while. Okay. So why is it R squared and not just R? Well, I think it's much easier to think of this in terms of the brightness effect of light. It's the same kind of idea if you have, a light that's projecting out into space or into any area, that as it moves one distance away, whatever that distance is, here we're going to call it R, there's a certain area that we call A that's going to absorb the energy of the light, or in this case, the energy of the gravity, if you will. And then if you go to 2R, what was 1 area before has become 4 areas. So 2 is now squared to show you how much area the impact of the gravity has to spread across from the same starting point, from the same generation of energy, if you will. And then if you go to 3R, you've got 9. Bob McGovern does a really nice demo on this with using light, but it's the very same principle. Okay, we're all familiar with that. We use this relationship all the time to understand how far away things are. If we know their intrinsic brightness and we can measure their observed brightness, we can use that kind of a law to determine how far away it is. Okay, forces of gravity. I'm going to keep moving the people around here. By the way, can you all see people as well as the screen, the slides? Okay, and then if you want to see more people, you have to put the little arrow. Okay, so the radius for the purpose of calculating the force of gravity is based on the center of gravity of each of the bodies. So they're centers of mass, not their surfaces. So we always measure from center of one body to the center of the other body, because that's how gravity acts as in a sphere, as if it's all the gravity is centered on that center of gravity, logically enough, right? Okay, so we're going to try a simple calculation just to check our understanding of the terms of this equation. Picture a planet, Krypton, with 1 moon, Farish, orbiting it at a radius of Z. Now Z, we're just arbitrarily calling it Z. Then there's another moon, same mass as Farish, but it's orbiting at a radius of 3Z. So the question is, how does the strength of the force of gravity on Woke, the more distant moon, compare to that on Farish? Okay, everybody want to do that quick calculation?
Are they the same?
What's that?
They're the same mass?
They're the same mass. And here's a little picture of it. So you got planet Krypton, you got Farish, which is 1Z away, and its mass is 1, and you've got Woke, and it's 3Z away, and its mass is 1. So how does how does the strength of the force of gravity on Woke compare to that of Farish? So who's got an answer?
Be 9 times.
One-ninth
Z
as
over 9.
much.
Z over 9. Or,
Yeah.
1/9 is great because it's the more distant planet is the one that's going to have the smaller gravity. Okay, now if Woke were 4 times as massive as Farish, so we've got the same, same deal. Krypton's the same, Farish is the same, but Woke is now a mass of 4. So in our equation, where does that increase go?
the numerator.
Numerator. Okay. So what would be the answer here?
4 times 1 is 4, divided by 9, 4 ninths.
4/9 is great. Okay. All right, and then just to make sure you got it, this one's a little more complicated, but not too much. Planet Vulcan is 3 times as massive as Krypton and has a moon, Spock, which is 5 times the mass of Farish. So instead of Krypton at what we called 1 before, and Farish, which is going to be, okay, so we got Vulcan, which is 3 times this massive, and we've got Spock, which is 5 times as massive. So that part is going to tell us what? How much more, if it was just that, how much more gravity would there be in that system?
15 times.
Okay, 3 times 5. But it's orbiting it at a radius of 10z, so 10 times the distance. So what's our answer now?
100 divided by 100.
So 15 100ths. Yeah.
Okay, 15 100ths. Everybody see that?
Yep.
Oops. In case you wanted to, in case you had any question about what we're doing there, we're taking the ratio. So we're taking the force of gravity of 1 in some simple terms. This one was where we made Woke 3 times the distance. So we add that in the denominator. And then if we take the ratio of those two quantities, everything drops out except 1/9, because all the terms are the same. And the same thing over here. Oops, sorry. Same thing over here where we increase the mass. Okay, everybody with me? And bored to death because it's pretty basic. But I guess I love things like equations and algebra. I didn't get too much farther than that, but it's very cool to think that it's that simple. That's what Isaac Newton gave us, was he understood, he discovered this equation for gravity, and it's very simple and straightforward, and it applies anywhere. We'll talk just very briefly about how Einstein kind of shaded that later, but Einstein's equation still works for most of the situations that we will ever need to deal with. Okay. By the way, any comments, questions? Okay, please speak up as we go along. What are the forces at work? Okay, so when something's orbiting, this is relating to orbit, I should say orbit, sorry about that. There's several forces working, but they balance. Okay, so if something is orbiting, here is a satellite orbiting the Earth, the gravity of the Earth is pulling it, is always, attracting it, and the item, which in case this case is a satellite, has a velocity, so it has some energy of its own, and it is orbiting because there is a perfect balance between the amount of momentum from this velocity of the satellite and the pull of gravity. And another way to look at that is on this other picture. You've got the planet, and it is really trying to keep drawing a straight line because of, object in motion tends to remain in motion unless acted on by a force, right? So that is what it would do, but it is acted on by a force, and that is a gravitational pull of the sun. So it's a balancing act. Down at the bottom, and I hope Michael Richmond will correct me on this if I say anything that's not right. The centripetal force is the force that force on an object to keep it moving along a circular path, and it is directed toward the circular object. So if gravity is pulling in, it's the combination here in this system, the centripetal force is what's keeping the satellite on a circular path. And there is a principle of conservation of angular momentum, which is a tendency of a system to preserve its rotational momentum in the absence of any outside or other force. So once an object gets into orbit with this balance between its motion and the pull of gravity, it's inclined to stay that way. Michael Wichman, do you want to jump in and say anything scholarly? If he's texting, you'll have to tell me what he
He
says.
says woohoo.
Thank you. I like that. Okay, what shapes our orbits? We'll talk a little bit later about the person who first said this, but the Greeks used to think everything was perfect circular motion. They were wrong. Almost nothing is perfect circular motion, and orbits tend to be ellipses. And if it were a circle, a perfect circle, now the Earth is somewhat close to a circle, but it's still got some eccentricity, which is the ovalness versus the roundness of this orbit. But whoops, sorry, clicking when I shouldn't. But everything that orbits tends to have an orbit that is not perfectly round. Now, we've been talking about the eclipse, some of us, a lot lately. How is the ellipticalness of the Earth's orbit or the moon's orbit? How are they important in an eclipse? Anybody want to answer that one? What is
Sure,
it?
they determine whether it'll be a total eclipse or an annular eclipse or just a partial.
Okay, if they were both perfectly circular orbits, and there wasn't any tilt to the moon's orbit, we both know about that part too. If they were both perfectly circular, what would happen?
It would be the same every time.
Every time, and have always be well, I don't know. I'm not sure whether it would always be which size, but it would be one or the other, and it would always be the same. Okay, so how are the relative masses of the two objects that are in a system of gravity, two objects that are attracting or in a gravitational system, how are their masses reflected in their orbits? So there are a couple of examples here. If the two masses were identical, like a two orbiting, like a binary star that happened to have pretty close to the same masses, their orbits would look like this. They're both orbiting on the same path approximately, but they're co-orbiting. Another example of co-orbiting is this one over here, where there's, this is a bigger binary star and a small, a star that has a bigger component and a smaller component. And you can see the kind of orbits, they're actually orbiting around the center of mass. And so this is the shape that those orbits would take. Now, I'm going to try to go to a simulation. I hope it works for you fine. If this doesn't move when I open it, please tell me, okay? Can you see me going to YouTube?
Yes.
Okay.
Yes.
Okay, so the center of gravity of the Earth-Moon system is inside the Earth. And so while the moon gets all that motion from the effect of gravity of the Earth gets some, but not nearly as much. So it's orbiting on a very small orbit. And they do say here that the sun-moon distance is not to what's the word I want? Not to
scale.
Thank you, not to scale. Whoops. I don't know why it does this, but it does. So I think, oh, there we go. So I'm going to close that one. Oh, maybe not.
Don't close that.
There, I think you're still there, right?
We're
Okay.
here.
Yep.
Okay, gonna keep going here. Now, if you're interested and care about such things, this is the way we would actually calculate or show the different effect of two bodies on each other. Anybody not want me to do this? A little more equations. So if you want to understand the gravitational influence of the Earth on the moon, what we do is we use two of Newton's equations. We take the gravity equation, which you're very familiar with by now, and we take his very basic force equals mass times acceleration. And if we set those two things equal, we can use it to find the Earth's influence on the moon and vice versa, and to see why the Earth's influence is so much greater on the moon than the other way around. So what we've got here, the Earth's gravitational influence on the moon its acceleration of the moon is, here's our equation, g times the mass of the Earth times the mass of the moon divided by the radius squared equals, and this is where we plug this part in, equals the mass of the moon times the acceleration generated by the Earth. And there, and down below the next one, the moon's gravitational influence on Earth is much smaller, because in this equation, when we do that, those are the terms that cancel out. And so you're left with the moon's gravitational influence on Earth is the mass of the moon equals the acceleration of the moon, proportionally. So I think I'll leave it at that. The whole gist of this is that there's mathematically, it's easy to see why one influences the other so much more. Questions, comments? Okay. Alrighty, this one's kind of fun. So 22 years ago or so, when I started studying astronomy, I had no clue that an orbit at a certain speed could only be at a certain distance from a planet. I thought, if you can orbit at one distance, you can orbit at a different distance at the same speed, but it doesn't work that way at all. They have to be synchronized. So this is about geostationary and geosynchronous orbits. So a geosynchronous orbit would be one where something is going around the Earth exactly in 24 hours, our period of rotation. A geostationary orbit is one that's at the equator, and it appears to keep the object hovering over one spot. If the period is 24 hours, so if there's something that's going to orbit Earth in exactly 24 hours, the radius has to be exactly this. It can't be any other radius to be geosynchronous. Now there is this pretty cool little applet.
Do you mean geostationary?
Which one did I say?
You said geosynchronous.
For what?
For it to remain at one point over the. Keep going, Carol. Sorry, never mind.
Okay. Geostationary is the one that remains
Yeah.
over one spot. Geosynchronous. We'll do a geosynchronous orbit that's not geostationary. So this is pretty cool. I like it. Let's do a geostationary near America. So, can I get up my button? Oh, yes. So that's what it looks like. The rotation of the Earth is exactly matching the orbit of the, whatever it is. Let's call it a satellite. And so the satellite appears to always be at the spot. And who's got the clock?
Oh, sorry. It's right next to me here. I'll mute. Well, we're done for another 30 minutes.
Is it time to quit? Okay, so that's the geosynchronous orbit.
No, geostationary.
Yes, thank you. Is that Nick?
Yes.
I owe you one.
No. I just want to make sure I get it because it's
You're
spaced in the
absolutely right.
same. It's spaced in the same space.
Geostationary says that it's very useful for weather, for example, so that they can always be looking at the same spot. But let's do a let's see, non-geostationary. Let's try this one. Okay, so there's that is not a geosynchronous orbit, as it says, non-geosynchronous. It's going right at the equator, like the same way the other one was, but it's not matched in time. Where's the one I want to find here? Polar orbit. Okay, let's try that one. So it would be possible to have something that was matched to the rotation speed of the Earth, but not at the right place. So if it's not at the equator, it's not going to serve that purpose. And in this case, this is a polar orbit. Do they have a polar orbit? Yes, polar orbit with time equals 24 hours. So that would be what it looks like. It's not very useful for being able to keep something in one spot, obviously, but there would be other great uses to that. So then I have to show you this because it's kind of crazy. look at this. They call this an unlikely orbit. Now, what do you think about that? Is it an orbit? And is it a stable orbit?
No, it seems to me like it would be, it would want to crash. Or
I-
fly away.
Right. What is going to keep it in this orbit is its own, if it's
Fuel.
got its own power and it's moving and it's got a lot of solar panels or something, then perhaps it could keep it moving in this direction, but it is not an orbit. Michael Richmond, you want to comment on anything?
Bogus.
Bogus, absolutely bogus, absolutely bogus.
Tony says if a theoretical space elevator was built, it would be in a geostationary orbit.
Can you describe that a little more plainly? What do you mean?
So there's an idea out there to build a space elevator to reduce the cost to put things out into space because it's very expensive to launch things. And so all the concepts that exist using carbon nanotubes, or there's a whole different number of, well, there's a handful of materials that could theoretically potentially have the strength to exist and to be like a tether that something could be put on and shot up this tether and then save the cost of using a chemical fuel to launch.
Okay. And does this particular unlikely orbit, impossible orbit, does it relate to that?
No, I said this a little while ago. It was about geostationary orbits.
Okay.
That's how I remember which one a geostationary orbit is, because I know the space elevator would need to be on a geostationary orbit because you wouldn't want your elevator moving where it was.
There's stuff to go flying around.
Yeah,
Yeah.
you'd want it near an island somewhere near the equator.
All right. So just so we are all clear, geostationary is one that is always appearing to hover over one spot on the globe, even though what it's doing is making a fairly big orbit so that it can stay in sync with the rotation of the Earth.
Okay,
So
I have a question related to that, if
Yeah.
I may interrupt here. If something is in a geostationary orbit, it is there because it has to be a specific speed in order to maintain its location right over that spot on the Earth. Like let's say a weather satellite or something like that. How accurate must that be? Wouldn't, if we started putting up a number of stationary objects that way, might they crash into each other because don't they all have to go the same speed? Or is that going to depend on their mass?
It's going to depend on their mass. It's not going to depend on the mass of the object, only because there's such a great difference between the Earth and the satellite. You know, that's not going to be a meaningful part of this equation. I can't answer that. Anybody want to weigh in on that?
Are all geostationary objects in the same orbit?
By definition, they have to be. Of course, you know, you could have
But
one here and one here.
yeah,
I mean,
right.
it can be a full array of them, but they're all going to hover over a different spot.
Okay.
And yeah, and there's no way to make it hover over a single spot other than by going at this exact speed that matches the rotation of the Earth.
And they'll have to be going that one specific speed.
Yeah. Yeah.
Yeah.
You remember a long time ago, this is Dave Bishop,
Dave,
when satellite dishes were huge and now they're getting smaller and smaller?
Yes.
The reason for that is because the satellites used to be in this really widely spaced. And now they're getting closer and closer together as they're putting more and more of them up there. And the reason why the dishes are smaller now is, number one, the satellites are more powerful, but they have to be aligned to only 2.5 degrees.
Okay. Okay.
In I'm not sure if this is answering your question or not, but in 2010, we lost control of one of the geosynchronous communication satellites. And it takes some control to keep it exactly at that geosynchronous spot. It started transmitting on full power and slowly wandered across the entire United States until it got over the Atlantic Ocean. Then somehow they regained power of it and put it back in position. So it does take a little bit of energy to keep them into that exact geosynchronous orbit, but not much.
Okay. And somebody controlling. Somebody
Yeah.
can make it happen. Okay. So again, what we said is to match a period of 24 hours, the radius of the orbit has to be exactly that. I mean, there's probably a few more digits. And that puts it in. What's
According
that?
to Wikipedia, there's 560 in geosynchronous or geostationary orbits currently.
Okay. All right. But they're each aiming at a different little spot on the Earth. Okay. All right. So any other radius cannot be geosynchronous. And again, the radius is from the center of the Earth. The altitude above the surface is 35,000
Right.
meters and change.
Carol, are the GPS satellites geostationary?
I don't know. Anybody know?
They are not. Believe it or not, I bid a geosynchronous satellite last week. Of all the funky things to say.
What do you mean? Good one.
I bid to build one.
Oh,
Korea and India India has its own set of geosynchronous satellites. The United States has their set, Europe has their set, and Russia has their set of geosynchronous satellites. Most of them are in low Earth orbit. And the way they work is you need to see 3 satellites sending out a digital pulse, and your little GPS unit takes those 3 satellites, and from those 3 satellites coming in different directions and at different Doppler shifts, it figures out where you are. What India does is India has its own version of GPS satellites actually in geosynchronous orbit. And it's got 2 in geosynchronous orbit, 2 above geosynchronous orbit, and 2 below geosynchronous orbit. So just north a little bit and south a little bit in geosynchronous orbit. And yes, they do cross each other.
Oof.
But that's how they do their system. And the system that I quoted for Korea was actually exactly that, but for Korea.
so you would be making this satellite and launching it?
We actually bid the transceivers for the satellite.
Okay. Wow. Pretty cool. Let us know how it goes.
I'll put it this way, I had to do a lot of research real fast.
Okay, we're going to keep going here. The other thing that my controls keep, let's see, Alt, no, my controls keep covering the top of the screen. But anyway, another effect of gravity is that it makes things, if they're big enough, it makes the spheres round. Into, I guess that's redundant. A sphere is round. The most recent definition of a planet, adopted by the International Astronomical Union, says a planet must do 3 things. It must orbit a star, okay? It must be big enough to have enough gravity to force it into a spherical shape. So that's another aspect of gravity we hadn't really talked about yet. And it must be big enough that its gravity has cleared away any other object of a similar size near its orbit. So it, as an example, over here there is Psyche, I guess that's how you'd say that, Psyche, which is a 140-mile diameter asteroid. It's supposed to be very metal rich, and they're hoping to capture it someday and be able to mine it. And here, you can see clearly it's not very round. I mean, it's somewhat roundish, but it doesn't have enough gravity to form it into a real sphere. Here is Ceres, which is classified as a dwarf planet. So obviously its diameter is multiples of, roughly right, four multiples of Psyche, and it is round. It turns out it isn't quite big enough to meet this last criteria, but it is big enough to meet this one. And then obviously if you go to any of the other bodies that are very round, Mercury, it does have enough gravity to do both those things. So over time, as planets are forming, gravity is going to pull equally and even it out into a beautiful sphere. But there's not enough for in an asteroid for that to happen. So that's why we see them the odd shapes that they are. Okay, checkpoint. I'm going to stop screen share for a minute so we can see everybody. Say hello. Everybody doing okay?
Yeah.
All right, good enough. Any comments, any questions, any interjections?
So these wandering planets that you hear about don't meet the definition of planets then, is that right?
Because they're not orbiting that, well, I don't know. Are they?
A
They're
particular
not orbiting
star.
the sun? Yeah. Yeah, they don't meet that definition. And what area would they have cleared out?
Mhm.
If they're wandering.
How much time do they give them to clear something out? I mean, is it, that seems like depends on when it was formed in the system, or is that clearing out done pretty quickly? The very last part of the definition of what makes a planet. Does it have a time frame on that?
Michael, you want to comment on the time frame for clearing out?
It's not clear.
Not clear. Okay, that's a good answer. They always say, I don't know, or nobody knows is a good answer. Okay. All right, I am going to keep going unless anybody wants us to just halt here, but I'm going to assume you're all having a relatively good time if you haven't closed out of the Zoom yet. 24, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Why did it say 20? Oh, there's 24 in the chat. Okay, 13 participants. I got it. Okay, so I'm going to go back to screen share. All right. Okay, so we're going to look at a little movie clip.
Great move.
The movie Space Cowboys. You may have seen it, but if you haven't, what's going on is there's these 4 older gentlemen who used to be astronaut types, physicists and all that. Some of them are pilots. And they're long since retired, but there is a very ancient satellite, well, Cold War kind of ancient, that is a Russian satellite, and it is starting to deorbit. And the problem is that it carries a bunch of nuclear warheads. And so they are trying to, they've gone up into space, they're trying to get control of this object. They're trying to make sure none of the warheads are released. And some collisions and accidents have happened, and it's not going well at all. So they need to figure out a kind of a, what do we do now? So hopefully I'm going to play this and we'll see what happens. And if there's a little ad, I apologize. Yeah, there's a little ad. It's short. Oh, skip ad. All right.
Share the sound.
Oh, sorry. I thought it. Oh. Let me stop share. Let me do a couple things. Escape. Stop. And go back to the beginning. Let me close it. Thank you for the reminder. Okay, so stop the share. Go back to share. Thank you. Important.
Zoom share with sound.
Yep, she's doing it.
Okay, let's try again. We'll probably get the ad again too.
Well, not if you paused it.
Now I reopened it, so.
Red Riding Hood loved visiting Grandma's
Now we got
house.
sound.
Unfortunately, others did.
This guy is a casualty of some of the accidents that have occurred.
Not getting much sound here.
Oh, really? Okay.
Can you raise the volume on the clip?
No chance of getting that thing into.
That's better.
Better?
That's better.
All right, do you want me to start it again, or you can get enough? They're trying to figure out a plan.
Even if we get this thing going, it's not gonna have enough power with 2 broken panels.
Take the kid back, I'll handle this.
And just how are you gonna handle it, Professor? You're a pilot, remember?
I'll need all the extra O2 modules you've got.
What are you talking about? No.
I love you, Frank, but why do you have to be such a killjoy all the time? Besides that, you ever see a prettier moon? What's he talking about, Frank?
It's 250,000 miles away. You'd never make it.
Oh, hell yes, I will. All I gotta do is get halfway there, the moon's gravity will take over and do the rest. I'll fire these things into outer space and let them self-destruct. That's not a solution, Frank. 1 PAM rocket's not nearly enough thrust. Now let's everybody slow down. There's gotta be another way.
There isn't.
No. Gotta be a winner in every race, Frank. Looks like it's gonna be me this time.
As usual, huh?
Oh, shit.
Okay. Let's see, there's another clip that I want you to see just so you aren't hanging about what happened to these guys. So let me do that one.
Red Riding Hood loved visiting Grandma's house. Unfortunately, others.
Looks like I'm getting the better part of the deal here, Frank.
Stop laughing. You used up all your oxygen, dummy.
Frank's hot wired it for you, but the trick is those missiles run out of fuel in 20,000 miles. You launch them too soon, the warheads could find their way back home to Earth. You leave it too late, well, it could run out of fuel and then you'd be stuck with it.
Is this gonna work?
I don't know. All right, fellers. Let's shoot this baby to the moon.
Count down to 1, right?
On a count of 1.
Okay. All right, so comments on the science portrayed there? Let's see, if you're speaking, I'm not hearing you. Is anybody saying anything?
There's not a lot of information on how much power those rockets have, so we really don't know what they're doing. To escape the Earth's orbit takes a lot of energy.
Okay, for sure.
And
Sure.
it looks like it's aimed straight at the moon. And wouldn't its momentum carry it? Wouldn't there be some angular momentum carrying it away from the moon as well as out to the moon? They'd have to steer it to the moon, wouldn't they?
Right, that's what he's doing. He's got a couple of,
Oh, that's why he had to, okay.
yeah, that's why he's got to do it, because it won't go by itself. He's steering it, which is a little hokey. But there was one very, very glaring.
He said halfways to the moon. Don't you have to get closer, inverse square?
You would certainly think. Yes, absolutely. If you get halfway to the moon, you're still much more bound by the Earth's gravity than the moon. So it's not going to keep on carrying you toward the moon. Okay, anything else? All right. I don't know. It's kind of a fun movie if you like old guys in space. So.
How would he possibly slow down?
He doesn't.
Yeah,
Right.
he doesn't. At the end of the movie, you see him in his spacesuit sitting on some rocks on the moon, and obviously he's dead. But you'd think he would have been kind of smashed to smithereens by the collision. So, okay, one more. This is Bruce Almighty. If you've ever seen this movie, Bruce has been given the powers of God by God. He's kind of trying to shake him out of his arrogance, I guess. And so this is the scene where Bruce Almighty is using it to manipulate the moon to his own advantage. I hope you can all stand Jim Carrey.
You could use that cloud clearing power.
Yeah, right.
Sure could.
I'm gonna bring him to the Space Breaks up on you. Tied to the rail. Yeah.
There we go.
Hi. Wow. Never seen the moon that big.
Okay, you can imagine where it goes from here.
Jennifer Aniston is an amateur astronomer. She has Schmidt-Cassegrain.
Oh, does she?
I think I had heard that too. That's pretty cool.
Yeah.
All right, so relating to gravity, what do you think about this clip?
Boy, the tides would have been a real bitch that day.
That's a good way to put it. Yep.
Well, evidently that moon doesn't have much mass because he was able to push against the rail in pulling it his way. So
Okay.
as the man says, it's only a paper moon.
All right, good one.
On the other hand, he's God, so.
There you go.
Yeah.
But what about him tying it in one place?
Yeah.
I'm not even sure of all the ramifications of that one. But it would stop. The tides would always be pushing and pulling one way. There wouldn't be the two tides a day anymore if he stuck it in one place. Anything else? What about eliminating some of these stars or adding stars? What do you think that might have done?
They're probably too far away, but I wonder if tethering the moon like that would have other consequences.
You'd think. You'd absolutely
You
think.
know, all of a sudden you're disrupting all these dynamics.
Right, right. I guess, the single biggest thing, obviously, that he's reducing the radius of the orbit and stopping the orbit, but let's hope he wouldn't be successful for long. Okay.
It would
So-
crash, right?
Yeah, the moon
It
would
would just
have to speed
it would
up
just
in order
ride
to
the rope
balance.
down and hit the earth.
Michael asked,
Wouldn't the moon would have to really speed up in order to balance the increased gravitational force by being that close?
that's right.
Very good. Thank you. Perfect. All righty.
Michael asked, "Are there any godlike movie stars on planets circling those other stars?"
We'd have to ask the SETI guys about that.
That's right.
Okay. Yeah, I'm sure they'd have some things to say about that. All right. I hope I get to play the recording later because I'll want to capture all the comments. I thought they're pretty good. Okay.
You didn't tell us we were going to be captured.
Well, I hope everybody saw that we're recording. At least we were, and I'll see that we stopped. Okay, so here's what I wanted to do real quick. I want to get you to give you a little perspective. If this were a full astronomy course and we were doing the whole, we would spend a couple of lectures talking about all these wonderful astronomers, physicists, mathematicians, whomever, who all together built on one another and sometimes had to contradict one another to come up with the true story of how and why things move and fit the story of gravity into it. So just to give you a quick timeline, each mark is 400 years. Aristotle, we're going to talk real brief about each of these people. Just a minute on each one, maybe not even, but just to kind of set the stage. And you'll see that from Aristotle, and then some 400 years later or so, there's Ptolemy, and you have to go a long way forward into the Renaissance time frame, just right about that time to start with Copernicus. And then there are three who overlap in their lifetimes very much, not perfectly, but they all lived somewhat at the same time. Tycho Brahe, Johannes Kepler, and Galileo, and then Newton soon after them. Einstein obviously had some things to say about gravity too, but I just want to do this real quick just to sort of put some of this in context, because we started out with Newton. We said, okay, Newton figured out gravity. He understood how it worked. He understood what was going on. How did he get to that? Well, he certainly had some preliminary work done by other people that helped set him up for that. Okay, so just quickly here, Aristotle is someone we look to because he had created a model of the universe that was 55 crystal spheres, all moving in uniform circular motion around the Earth. That there was perfection above the realm of the Earth, and there was imperfection down below. At that point, the Greeks had no understanding. Can somebody mute that? Somebody's got their TV on or something.
Let me see.
Thank you. They couldn't understand how the Earth could not be the center because they're watching the motions in the sky and they're just not, it doesn't make sense to them. But they don't think the sun can be they don't think the sun can be the center, because Earth, if that were the case, then when Earth goes through its yearly orbit around the sun, that would make the star positions vary because of parallax, and they didn't observe any parallax in the stars. So they thought, okay, that can't be what's happening. And also, not understanding gravity and forces and such, they thought that if the Earth were rotating, then that was the cause of day and night, that we would fly off or we would feel a very violent wind. Aristotle also he didn't really understand forces, and he thought there were, at that time, he and the other Greeks thought there were 4 earthly elements: earth, air, water, and fire, plus the ether of the heavens, and that that the motions were about elements striving to their natural placement in the universe, so that earth and water fall and air and fire rise. Completely different, obviously. Brilliant in its own way, because they had to start somewhere, but very different from what we know today. And then about 400 years later, Ptolemy came along and he created a picture of what's going on out there. And his model was geocentric. The Earth was at the center. And he understood that the planets move on around the Earth, and that in order to replicate the retrograde motions of the planets, he had to make it a little fancier. So he added some things called epicycles, on which the planets would actually move in order to try and create that sense of retrograde motion. Clearly the model's wrong in major ways, but it made fairly good predictions of what was going to happen. And by the way, it was accepted for 1400 years without people having a replacement for it. His book was the Mathematical Syntaxis, however you would say that in Greek, was labeled Almagest, or the greatest, by the Arabs, who became astronomers in some of the centuries after that. So again, he had a great influence on the understanding of what was going on in the motions of the universe. Okay, skip way forward, almost to the Renaissance, or into the Renaissance, and Copernicus comes along. He comes up with a very different model, and he puts the sun at the center. And he published a document about that. It was a bad time for someone to be spouting theories like this, that the sun was at the center, because the Catholic Church, for one, was quite opposed to that view. The Earth was supposed to be the center of everything. And whether it was because he feared the church and the Inquisition, or whether it was because he just didn't want to be ridiculed when everyone else was thinking that the Earth was the center of the universe, he didn't publish until he was about to die. But obviously his model is much clearer to what's happening today and what we know to be happening today. So he understood that the planets move with orbits about the sun, but he thought they were constant circular motion, because he still maintained that idea from the Greeks that the motion should be circular, and a perfectly circular motion. He did understand that the Earth spins on its axis. So, okay, then we move forward, and everyone knows the stories of Galileo, who made great strides in this whole thing. He believed Copernicus, and he actually found 4 kinds of proof to back up Copernicus' model. That was seeing the craters on the moon and realizing that it wasn't perfect, seeing the phases of Venus, which could only be replicated if it were orbiting the sun. He saw the Galilean moons orbiting Jupiter, and therefore was able to understand that other things are orbited besides the Earth. And he observed sunspots on the sun and realized that it was not perfect. So again, it was against that original old model of perfection above the realm of the Earth. He did believe that the sun was at the center, and he tried to say that, and the Inquisition said, no, you really aren't going to be allowed to say that. So he spent the rest of his life on on house arrest after that. He also did some experiments, and he proved that objects fall at the same rate due to the force of gravity, regardless of their mass. So if you had 2 objects and you drop them, we've done this at summer camp. If you have a light object like a feather and a heavy object like a bowling ball, and you can take friction out of the equation, you would understand that they are falling at exactly the same rate due to the force of gravity. So these are all contributions that Galileo made. And then we come to Tycho Brahe, and that's how it's usually said in astronomy classes. My Danish daughter-in-law says it as Tycho Brahe. So I'm not really sure that we're saying it anything close to his real name, but he was someone who made huge strides in observation, naked eye. And he was able to observe the planets and capture very, very detailed data on how they move. He had a somewhat different model of the universe, but it wasn't particularly well accepted. So we don't really need to focus on that too much. He was given land by the Danish king to build an observatory. And Don is going to tell us a little bit about that. But the most important thing about him is he made meticulous, extremely careful, extremely accurate, naked eye observations of planet positions. And he had an assistant, Johannes Kepler, who used that data to formulate some new laws about planetary motion. And this is Kepler. He was a brilliant mathematician and scientist in his own right, but he brought him on to work with him because he saw his mathematical skill. Tycho was very jealous of his data, and he didn't want to give Kepler all of the best data because he knew that Kepler was likely to draw some conclusions, and he himself wanted to be the discoverer. But it turned out that when Brahe died, Kepler was able to get that data, and because of it, that's when he was able to produce his 3 laws of planetary motion, which we see as a great move forward. He didn't understand why things moved the way they did, but he was able to describe very accurately how they move. And then we talked about Newton's universal gravity equation. There's probably lots to say about Newton, but the most important thing is here, he came up with the laws of motion, his inertial force and equal opposite forces laws, and the gravitational law. And he knew all of the works of Copernicus and Kepler and Galileo. And so he had that information as he went into his process of understanding how things move. Albert Einstein, that would be a talk for a whole nother night. But he obviously came up with a whole new idea of gravity much, much later, which is that matter energy tells space-time how to bend, space-time tells matter energy how to move, and a good visual that suggests what that like is this one on the side where 3 masses of different masses are each bending space-time in different ways. And the conclusion is that gravity is really not so much a force as this bending. But again, that's something that we'll have for a whole nother time. Okay, so I am going to stop my share, and I am going to, let's see, I didn't yet make you a co-host, Don.
Okay.
Let me do that right now. I think I can do that over here. Make you co-host. Okay. Yes, so you should be able to share screen now, Don, okay?
Okay, let me do this, and I've got to set this up slightly. Share. And we will start from the very beginning. Won't we?
So.
Here we are. Yes, we go. Okay. Tycho Brahe, the way we pronounce it, not the Danish. He was given this island as a fief. And I should mention, he was given that by the Danish king, Frederick II, I believe it was. And so at that time, it was spelled F-V-E-N. However, the island is now within the territory of Sweden, so it is spelled V-E-N. Anyway, this is somewhat of a view. Tycho was given this as a fief, and so he had residents who lived there and worked there, and he required their services 2 days a week to come and work for him. And he was a bit of a taskmaster as far as that goes. But he was active there for about 21 years. So we're going to talk really about what was happening during that period of time. You may visit this today yourself, either by coming from Sweden or from Copenhagen. And this is basically a little map that you can get when you rent bicycles. It's a wonderful little island there, 2.7 miles long by 1.4 miles wide. And there are about 400 people that live there today. Now, here's the location of where it's at, Copenhagen. There are daily boats that go out to it, and Sweden from the other side over there. A very nice trip for you to go. Once you get on your bike, and you can walk it if you like, but hey, why not ride a bike while you're there? Do it Danish style as far as that goes. You'll come across a very nice location. Unfortunately, there is next to nothing left of the buildings or anything else when Tycho was there. In fact, soon after he left the place in, what was it, 1597, they started tearing his mansion apart and using the building materials someplace else. And so there's essentially nothing left. But today there are a few buildings that are there. I might comment very quickly on one of them, which I believe is number 4. And I can't read it because it's in Danish. But anyway, or 8 anyway, it's this one up here, I believe. He was so secretive and so protective of what he was doing out there. He was afraid other people would steal his ideas and get credit for them. And so he built a paper mill and printing press so that he could print all of his stuff. And he supervised every single page that was set in type and turned out from there. So he was a bit paranoid in a number of different ways there. But there is today laid out, and you will see, we'll show you some pictures of it. This was the area where his mansion was located, and his mansion was located here in the center. It was surrounded by a Renaissance garden that was there, and the Renaissance garden, I didn't pay a lot of attention to that. They are planting it today with plants that would have been available in the late 1500s when Tycho was living there. And there was some significance about the choice of plants and everything else, but I didn't get into that. The main area that we're going to look at is this long building, which is a church. And then we will end up by coming farther down here to an interesting concept, an underground observatory. More on that later as we go along. As you approach, you will run into this church, and this is where we're going to go into now, because the main display for what we're interested in and the type of equipment that Tycho used is to be found in this church. It's a church that is now being used as a display, and some of the local kids, or I don't know where they came from, either Sweden or perhaps they came from Copenhagen or Denmark on the other side. But anyway, the school groups come through there, and essentially that's what it looks like. Here are some of the instruments. They don't have a lot of them there, but for our purposes, we want to see essentially what they look like. This was a sextant that he had designed and had made by craftsmen. Incidentally, these are not the originals. The originals, for the most part, have been lost. After he left there in 1597, he went on to be the mathematician for Rudolf II in Budapest, and he took these instruments with him, but they have disappeared. But these have been reconstructed according to pictures that they have found before, but they've done an admirable job. So this is a sextant, and it was used to measure the angles between objects that they can look at. Now, I could not read and understand how this was to be done, because it was printed, I don't know, either in Swedish or Danish. I'm sure they're very close to each other, but it's kind of interesting to see what it was made of. There were evidently these sighting areas right here, and you can see it slips along the arc right here and along this side. Why there are two of them, I guess I don't understand, and why there are two slits, one or the other. I don't know, but no doubt you look through here and a line on something at the far end or from here, and now you can measure angles. And the great thing about it was when he did this, his measurements were 10 times better than anything that anybody else was able to do. And it was attributed that he could do it to an arc of around 15 degrees of 15 seconds of arc. That was the accuracy of it. And kind of an interesting mounting effect that he had right there. Lost Mandy evidently wasn't around at that time to give him something better on there. This is another tool that he had, and this was a quadrant, and it measured the altitude. And I think you kind of get the concept of that. A couple more pictures of it again, but you can see there were, it was made with wood or steel and marked off with various measurements, various degrees and so on. And this could be used. Once again, there is this slit and this slit. And so I don't know, maybe he's comparing things for that purpose. I'm not sure. Anyway, other close-ups of what that was. This was the quadrant. Now, he had a number of other instruments that they did not have on display there, because that was probably enough for most of the public that's there. As it turned out, his measurements were very, very good, as I said, 10 times better than anybody else. While he believed in Copernicus and followed Copernicus, he still held to the idea that everything revolved around the Earth. And it was, I can't pronounce it, but it was earthocentric. I guess I can make up that term. But anyway, everything was moving around the Earth, including the sun that was out there. So he still held to that idea. Here is a drawing of what Uraniborg Castle looked like, and with the gardens around it and everything else. Now, none of that exists, as I say, but they did have a model of what the mansion looked like. And this is a very interesting concept, and I think gets down to the importance of Tycho Brahe. And that is this. It was made, I won't go into all the detail. He and his family lived in about a fourth of this mansion. However, the mansion also had libraries within it. It had meeting rooms in it. It had smaller rooms that were people were capable of staying for quite a while. And he invited other scientists to come there. So really, this was about the first scientific institution that had been established. Now, part of what you will see, if I can find my cursor, which has gone away somewhere. Where are you? Here it is. Okay, one of the things that you will notice are these unusual observing areas all around here, up on top and to the side, so that they could be used by various people at the same time while they were there. But you might notice a number of these sit on pedestals out here, and they're kind of stuck out on the edges of the building. Well, that caused a problem. It caused a problem because they were not stable and they were affected by the winds quite a bit. So he moved a little bit farther away, and he built this thing that is an underground observatory. Now, this is kind of what they have built here is something. Come on, cursor, where are you at? There you are. Okay. They have reproduced here kind of what they think it might have looked like. They don't have many pictures of what it was. There was some archaeology done a number of years ago, back in the 1920s, I believe, and they have tried to recreate things that were here. Well, today you may go into there, wait your turn, and a small number of people, about 8 or 10 at a time, can go down below the big dome. And once you get down there, they've dug out the dirt and you can see a few things down there, and they have a spotlight show that will point out objects or direct your attention while a narration goes on and explains about what was going on down there. But it looked something like this. It had a dome on it. I haven't read whether that dome turned. I would think it had to, but certainly it had places where you could look out from there. And as a result, he got away from the wind. And I would also think in the wintertime, he was able to get away from some of the cold down there. So that's what he tried to do, was improve those conditions. And that brings us to the end of what he was doing. Any questions? Well, that's okay.
Don,
Don, when
What-
you went to the tour, it was in Danish or Swedish, right?
I don't know. I don't know Danish from Swedish as a language. I'm sure there are many things that were very close, as they are, but I don't even come close to Danish.
Don,
Yes.
was there a record kept as to how many clear nights they had in that part of the world?
No, no, there wasn't
anything done. I would
yeah.
imagine the weather pretty
Yeah.
bad.
The weather
Well-
sucks. The weather sucks there. My Danish daughter-in-law moved part of her family to Spain. So,
Well, it's sitting out in the middle of that sound there between the two countries. One thing too that I do want to mention to you, in all of that you have seen, you did not see a piece of glass. He did not use lenses and things of that nature. He himself died 9 years before the invention of the telescope.
Oh,
So, that was all straight observation with a naked eye.
amazing.
it
Well, thank you,
truly
folks.
is amazing. Thanks, Tom.
Yeah.
That was great.
Go
So
ahead.
you were there a number of years ago, right?
Yeah, 2014, I think, 14 or 15.
Probably hasn't changed. I visited there once too, and I remember being just blown away by the fact that the observatory was in the ground, but it seemed very
Yeah.
logical. Seemed very
Well,
logical.
it's a delightful little day's tour. If you're ever there, plan on going and walk and ride your bicycle around the island. And there's a lot more story to be told, no doubt.
Thank you. Thank you. Kepler is just, both of them, Brahe and Kepler, just did amazing work. And since Don had been there and had such good pictures, I definitely thought it was a nice addition to our story of how everyone came to understand the motions of the heavens and the forces that are involved and such. I have 5 minutes to 9, so I think we are kind of at the point where we are going to wrap up. I'm sure you've all been sitting long enough. We do have some stuff we haven't gotten to, but maybe we'll save that all for another time. Any comments, questions, offers to host the next one?
This was good, Carol. I enjoyed it.
Thank you.
Yeah, it was terrific. I really enjoyed it too.
Yeah, thanks, Carol. This was really nice.
Great.
I learned
Great.
something.
All right, good. That was
Very good,
cool.
Carol. I wish more people would have had a chance to see it.
Yeah, well, we did record it, so maybe we can somehow give them a sense of what's possible here.
Carol, I can
yeah.
give you the credentials for our YouTube page if you want. There, yeah.
Okay, good. Yeah, please. Okay, all right. Well, thank you all for being part of it. I enjoyed it. I hope you did.
That was fun.
Thank you.
That was fun.
Yeah, thank you very much, Carol.
This.
Yeah,
Look
it's
forward to the
very
next
cool.
one.
It reminds me of that long time ago when you and Frank did Astronomy 101. We had a whole sequence of lectures and stuff, and
did.
learned a lot.
We did.
And yeah, thank you very much.
Yeah.
Yeah, thanks, Carol. That was a good review of some of the basics on that. I'll look forward to seeing more as we go along.
Okay.
The Adirondack Club, this is Dave Bishop, the 80K Club has asked me to do some Astronomy 101 talks for them.
Cool.
And I've actually resurrected some of the talks we did back in the day
Okay.
to do for them.
I still have all my notes if you want to see them.
I bet you do. Yeah, well, Dave will be putting you on the schedule for these, okay? All right.
Actually, I'd like to have a lot more from talks from our own people instead of talks from external speakers. It's great to have something like this as a mix-up, because having some professor every month gets boring after a while. Frank Bob is actually doing an Astronomy 101 talk for January.
Good.
Just
Right
so you
at the,
guys
at
know
the
that.
general meeting?
Yes, general meeting.
Okay. 'Cause, you know,
And David, I'm sure you meant to say that having college professors, except for Michael.
I was expecting to see a
Always
comment from him.
He baited me, so I baited him.
Right?
Oh,
It's only
no.
fair.
Dr. Richmond is very entertaining. I thoroughly enjoy when he talks.
Yeah.
By the way,
Absolutely.
just for those of you who are here, be prepared in December. You are going to be challenged at his talk in December at the planetarium. So get your calculators and your pencils, have them ready. Yes. He
He's not going to ask us to run.
Calculators. That's awesome.
He's not going to ask us to run down to the bottom of the auditorium or anything like with Nathan.
Right.
Nathan Markle, Lee Markle's son. He's like, come down here, you'll be a star.
That's
Ran
right.
down through. That was awesome.
As far as Michael's challenges, what does that say? Nope, nothing like that.
Nothing like that. Just determine.
Okay. So,
Okay, good.
having taken a course at RIT from Michael, I loved the course. But one of the things I liked a lot is that Michael always adds those challenges. You know, he'll teach you a bunch of stuff and then he'll say, okay, now go use it. And you're like, what? I remember the time he had us calculate the age of the universe from the Hubble constant. It was like wow, we just sat there and did it. Long galaxy, so many of them out there. Okay. All right. Hey, listen, thank you so much for coming. Any feedback you want to send me by email, I'd love to hear it. And I'll see you again.
Thanks, Carol.
Thank you.
Thanks a lot.
Good night, all.
Good night.
Good night. Thanks, Carol.